So we were discussing about the vectored interrupts of 8085. Just to revise the things related with the interrupts of 8085, we already know that there are 5 interrupt lines which are available in 8085. And these 5 interrupt lines are INTR line, RST 5.5, RST 6.5, RST 7.5, and the trap. Now, trap is a non-maskable interrupt, and rest of the interrupts are maskable interrupts. Out of these, the RST 5.5, 6.5, 7.5, and the trap, these interrupt lines are automatically vectored interrupt lines. Automatically vectored interrupt lines means if any device which is connected with these lines wants to interrupt the operation of 8085, then it automatically transfers to the specific memory location designated by page 00. And these memory locations are, if any device is connected with 5.5, the memory location is 002C, where the subroutine is written, which will be executed. RST 5.5, 0034 is the memory location where the subroutine is written. If any device is connected with RST 7.5 and it is interrupting the functionality of 8085, then the memory location is 003C, where the subroutine is written. And if any device which is connected with trap, it is automatically going to the 0024. So that is why these interrupts are called vectored interrupt. There is no need to insert any instruction to execute the service subroutine. But whenever any device which is connected with INTR line wants to interrupt the operation of 8085, the device has to assert RST code. And we already know that we have 8 RST instructions which are made for that. And so in case of INTR line, if any device is using INTR line, it is the responsibility of that device to assert the RST code. And depending upon the assertion of RST code, it will go to the location either 0000 or 0008 or 0010 or 0018, 0020, 0028, 0030, and 0038. And these locations are specified for the individual instructions which are being asserted by that device. If it is asserting RST 0, it will go to the page 0000. If it is asserting RST 1, then it will move to 0008 and so on. So it means these 4 are vectored interrupt, and this is not a vectored. For this particular case, the device has to insert the code, and depending upon that code, the location will be specified. So this is the difference between INTR line and the rest of the lines. Now, as far as the other interrupts are concerned, this is the basics of the interrupt which we have already discussed. We already know that 2 types of interrupts are there, maskable and non-maskable. Maskable interrupts can be avoided for a few times, and non-maskable interrupt has to be entertained immediately whenever it is being received. We also know the hardware and the software interrupt. Just I have given you the example. RST instruction, if it is inserted in a program, then that is a software interrupt, and the rest of the interrupt are the hardware interrupt. We also have discussed about the instructions which are used to enable and disable the interrupt. For that, we will be using EI instruction and the DI instruction. And these are the restart instructions which are used to insert, which is going to specify the call location where the service subroutine has to be executed after the RST instruction. An individual RST instruction have its own hex code or the mnemonics code. Oh, sorry, hex code. This is the mnemonics code. This is the hex code of the individual instruction. That is what I am saying, that if trap is connected to a particular device and wants to interrupt, it will directly go to the location 0024. There is no option at all. But in case of INTR line, there is an option either by asserting a particular interrupt instruction. So let us now, as I told you, that RST 7.5, 6.5, and the SARIA 7 5.5. These are the interrupts which are the maskable interrupts. And these maskable interrupts can be masked by using instructions, by writing something into the content of the accumulator, and then, so meaning thereby individual interrupts can be masked, or one of the interrupt can be masked, or more than one interrupt can be masked. And this can happen in combination with another instruction that is called set interrupt mask. So as far as 7.5, 6.5, and the 5.5 interrupts are concerned, they are known as maskable interrupts. They can be masked, they can be unmasked. And the masking of the individual interrupts can be done by enabling the by enabling the instruction EI as well as set interrupt mask. Set interrupt mask is another kind of instruction which is used for either setting or resetting the individual interrupt lines. Now, the execution of the set interrupt mask is going to either enable or disable the interrupt according to the bit pattern of the accumulator. Depending upon the value of the accumulator, we are going to either mask the individual lines or not. And disable DI instruction is used to disable the interrupt, but it is not always required because we don't want all the interrupt to be masked at the same time. We want only, if we want only few of the interrupt line to be masked, then we can do it with the help of SIM instruction, that is SIM instruction. This is the SIM instruction, that is set interrupt mask. Set interrupt mask is a single byte instruction. And the purpose of using, this is single byte instruction, and the purpose of using set interrupt mask is to read the content of the accumulator, and depending upon the content of the accumulator, it is going to either enable or disable the interrupt. Whenever 0 is there, it means that interrupt is available. If 1 is there, it means it is masked. So let us see, let us go with the, what is the pattern of the accumulator depending upon which we are able to access whether which interrupt is masked or which interrupt is not masked. This is 8-bit, and this 8-bit represents the content of the accumulator whenever set interrupt mask instruction is being executed. So what does this mean? The D0 bit represents masking of 5.5, RST 5.5. The bit number D1 is representing masking of 6.5, RST 6.5. Bit number 2, D2, represents masking of RST 7.5. And this D3 represents whether the mask is set enable or not. This is a special bit, that is D4 bit, which represents the resetting of 7.5. Besides setting and resetting from this, you can also do with D4 bit. The D5 bit is undefined or unused, and D6 and D7 bits are used to enable the serial input and output. So that is what is written, that bit number D7 and D6 of the accumulator are used for serial input output, and it is not going to affect the interrupts. If D6 bit means this bit is 1, it enables the input output because this is SOD enable. serial output input output enabling. Now, bit D3 is a control bit. This D3 is a control bit, and it should be 1 whenever we want to set or reset, whenever we want to mask or unmask the individual RST 5.5, RST 6.5, or RST 5.5. This has to be 1. D3 bit should be 1. If D3 bit is 1, then only the bits which are available at D0, D1, and D2 will be effective. Otherwise, if D3 is 0, then in that case, whatever is the value of D0, D1, D2, it is immaterial. Now, logic 0, if it is logic 0, it is going to enable the corresponding interrupt. And if it is logic 1, it is going to disable. It means if MSC signal, if MSC, that is mask set enable, that is D3 bit is 1 and D0 bit is 0, it means RST 5.5 is available. But if D3 bit is 1 and D0 bit is 1, it means RST 5.5 is disabled or masked. So for making RST 7.5, 6.5, and 5.5, whether they are masked or they are available, it is necessary that D3 bit should be 1. And if D3 bit is 1, if all these 3 are 0, it means every interrupt line is available. If one of them is 1, it means that is not available. If 2 are 1, it is that not available. If all are 1, then it means it is not available. Now D4 is an additional control for RST 7.5. That is what I have said. Besides D2 bit, which is going to make it available or not available, besides that, if we want RST 7.5 to disable, reset, then D4 should be 1. If D4 is 1, RST 7.5 flip-flop is reset. And this is used to override RST 7.5 without servicing it. If this is 1, whether it is 0 or 1, it is immaterial. If RST 7.5, that is D4 bit is 1, it means RST 7.5 is disabled. So what the functionality of set interrupt mask instruction is, before we want to use set interrupt mask, what we have to do, we have to load an 8-bit number into the accumulator, and then whatever number we are loading into the accumulator, depending upon which interrupt line we want to mask and which interrupt line we don't want to mask, want to make it available. So before using set interrupt mask instruction, we must have to load a certain value into the accumulator, and depending upon that value, the individual interrupt lines will be available or it will not be available. Now, as it has been told that the entire interrupt process, except the non-maskable interrupt, that is trap, it can be disabled by resetting the interrupt enable flip-flop. It can be reset by using instruction DI. If DI is used, every interrupt line is disabled except the trap. Or if we are resetting, every interrupt line will be disabled. Or if the processor has recognized already an interrupt request, and since it is entertaining the interrupt request of a particular device through any interrupt line, it is going to automatically reset the interrupt enable flip-flop. So besides that, we have 3 more ways by which we can set or reset the interrupts. But all these processes are used to reset all the interrupt lines. Now let us go into the programming which is related with the interrupt of 8085. Suppose it is asked you to enable all the interrupts. so that all the interrupt lines will be available. Now, SIM instruction is meant only for RST 5.5, 6.5, and 7.5. It is not at all concerned with the INTR line or trap line. Trap line, because trap is a non-maskable interrupt. It cannot be disabled or it cannot be enabled. It is already permanently enabled. So if it is asked to enable all the interrupts of 8085, well, we have to do very simple things. First of all, we have to enable all the interrupts by using EI instruction. And then we have to put something into the accumulator so that all the interrupt lines should be available. Now let us go and check. If we want this, and this to available, it means this should be 0, this should be 0, this should be 0, because 0 is going to 0 stands for that these interrupt lines are available. So if we want to enable all the interrupts, all these three must be 0, means D0 bit must be 0, D1 should be 0, D2 should be 0, as well as the mask set enable should be equal to 1. So it means 1, 0, 0, and 0. And since we don't want to reset the RST 7.5, so what it will be? It will be 0. And this is unidentified, so this will be 0. Since we don't want any kind of serial input and output, so this should be 0. And this should be also 0. So 0, 0, 0, 0. It means 0. And this is 1, 0, 0, 0. It means 0 and 8 should be into the accumulator if we want all the interrupt lines to be available. So that is what has been done. MVI A08, get accumulator bit pattern to enable RST 7.5, 6.5, and 5.5. So by loading 08 into the accumulator, we are getting enabling process of RST 7.5, 6.5, and 5.5. And it is not only by loading these interrupt lines are going to be enabled. It is the instruction SIM, that is set interrupt mask. It is then whenever it is executed, then only it is going to enable RST 5.5, 6.5, and 7.5. Let us go with another example in which it says enable 6.5 and disable 7.5 and 5.5. We want only 6.5 to be available and we don't want 7.5 and 5.5 to be available. So for that, what we have to do, if we want 5.5 to be masked, so it should be 1. If we want 6.5 to be available, it should be 0. If we want 7.5 to be masked, so it will be 1. So 1, 0, and 1. And this should be 1 because mask set enable signal should be 1. We also want RST 7.5 to be disable. So this bit should also be 1 and the rest of the bits will be 0. So what will happen? What we'll be doing? We will be loading 1D into the accumulator. 1D, why? So what will be this one? 1, 1, 0, and 1. So it means 8, 4, and 1. 13. 13 decimal is equivalent to D. And this should be 1. So it is 0, 0, 0. So it means 1D. So that is why 1D has been put into the accumulator. Now, suppose that we want 7.5 to be available and 5.5 to be disabled. What will happen? We want 7.5 to be available and rest to be not available. It should be masked. So if it has to be masked, so it will be 1. It has to be masked, it should be 1. If it is to be available, so it will be 0. If it is to be, if we want any interrupt line to be masked or not masked, we have to put this 1. So 1, 0, 1, 1. It means 8, 2, 1. 8 to 10, 1, 11. A, 10, B. So this bits D3 to D0 will be B. We want this RST 7.5 to be available. We don't want to reset. So what we'll do? We will put it as 0. So it will be 0, 0, 0, 0, and then it should be 1, 0, 1, 1. So it will be 0 and it should be B. So 0B we will be putting into the accumulator, and then we are using the instruction set interrupt mask. So this is how by writing certain instruction, we can program it. We can write we can write a program using interrupt enable, which will be enabling all interrupts, and then copying a certain binary pattern into the accumulator so that individual interrupt lines, that is of 7.5, 6.5, and 5.5, can be enabled or can be disabled by using afterwards the set interrupt mask instruction. Now, the pending interrupt. What do you mean by pending interrupt? When one interrupt request is being served, interrupt may occur resulting in a pending interrupt. It may be possible when one interrupt request is being served by the processor, other devices through other lines or the same line might want to interrupt the processor. So while it is handling one interrupt and other interrupts are coming to the processor, those interrupts will be called pending interrupt or the pending request. When more than one interrupt occurs simultaneously, the interrupt which is having the higher priority is being served first, and the interrupt with the lower priority remain the pending. So pending can be done in two ways. If more than one interrupt lines are coming all together simultaneously to the processor, processor first of all will handle only that interrupt which is having the highest priority, and the rest of the interrupts will be pending. The second case of pending interrupt may be if one interrupt has come and it is being entertained by a processor, and processor is entertaining that interrupt, and during its execution, another interrupt arrives at microprocessor. So that will be considered as a pending interrupt. As 8085 contains several interrupt lines, we have 5 interrupt lines in 8085. So it may be possible that an interrupt may occur while other interrupt is being served, resulting in a pending interrupt. This possibility is used to happen in 8085 because of many interrupt lines are available. The 8085 has an instruction. By using an instruction, read interrupt mask. So 8085 has an instruction, read interrupt mask, that is RIM, using which the user or the programmer will be able to know the current status of the pending interrupt. Now, 8085, which used to use the instruction RIM to know the pending interrupt, this instruction gives the current status of only the maskable interrupt. In case of INTR, the processor reads its status in the last state of the last machine cycle of an instruction. When the processor returns to the main program after serving the interrupt service subroutine, it knows the status of INTR line as soon as it makes further execution of the main program. So the difference is, if any device has asserted an interrupt through an INTR line, and it may be possible that there are many devices which are connected with the INTR line. So whenever any device which has asserted interrupt through INTR line to the processor will be executing its service routine depending upon what kind of RST instruction it has asserted. And while RST instruction has been asserted, it will switch over to the interrupt service subroutine, which is written to a specific memory location. Now, while returning from the service subroutine to the main program, it will check, is there any pending interrupt remaining at the INTR line? And that is what I want to say, that read interrupt mask is going to read only the pending status of 6.5, 5.5, and 7.5. It is not going to check the pending status of INTR line, because INTR line is different from 5.5, 6.5, and 7.5, because INTR line does not belong to the category of the vectored interrupt. So let us go and see how this read interrupt mask used to work. Now again, this read interrupt mask is a single byte instruction. And before using the read interrupt mask, it is going to load the accumulator with an 8-bit which indicates the current status of the interrupt mask, interrupt enable, pending interrupt, or any kind of serial input and the output. Now here you can see, again, bit D0 represents 5.5, bit 1 represents 6.5, bit 2 represents 7.5, bit 3 represents interrupt enable flag, bit 4, 5, 6 represents the pendency of the interrupt, and set interrupt serial input data is represented by D7. So from bit D0 to D2 for the interrupt mask, these bits are used for the interrupt mask. If it is 1, it is masked. If it is 0, it is available. Bit 3 indicates the interrupt enable flip-flop. If it is 1, it is enabled. If it is 0, it is disabled. Bit D4 to D6 indicates the pending interrupt. If it is 1, it means these interrupts are pending. If it is 0, no interrupts are pending. And bit 7 is the serial input data, if any. If there is any serial input data, it is being represented by bit 7. So after executing the interrupt service subroutine, the processor checks whether any other interrupt is pending by using the instruction RIM. If any interrupt is pending, the processor executes its interrupt service subroutine before it returns to the main program. Meaning thereby, I'm giving you 2 examples. Suppose there are 2 devices which are connected with INTR line, and one device has made an interrupt request, and that interrupt request is being entertained by the processor, and that device has asserted an RST instruction, and its service subroutine is being executed. While now once the service subroutine has been executed, it has to return to the main program. But before returning to the main program, it will check whether there is any other interrupt, whether there is any other device who has interrupted through INTR line. If it is so, before returning to the main program, it will first entertain the interrupt. And by entertaining the interrupt, it will be that device will be asserting an RST instruction. And again, it will switch over to the next instruction subroutine, interrupt service subroutine. Similarly, in case of 5.5, 6.5, and RST 7.5, there is a possibility while 6.5 has asserted an interrupt line and interrupted the process of the processor. So RST 6.5 has asserted through a device. So it means RST 6.5 corresponding interrupt service subroutine will be executed. Before returning from the service subroutine to the main program, it will check the pendency of any interrupt line through this instruction RIM. So RIM instruction is mainly used to check the pendency of 5.5, 6.5, and the 7.5, and how it is being done. Now, going to give you an example, and this example will give you the idea. The problem says that assume microprocessor is completing an RST 7.5 interrupt request. Check to see if RST 6.5 is pending. If it is pending, enable 6.5 without affecting any other interrupt. Otherwise, return to the main program. So while microprocessor is entertaining 7.5, we can use an instruction RIM to read the interrupt mask, whether any interrupt is pending or not, like this. If any one of this bit is 1, it means this is pending. So what we'll do, whatever is the mask information available in the accumulator, it will be copied in the B register. And since we have to check the pendency of only 6.5, whatever is the content of accumulator, we have to check only the pendency of 6.5. So pendency of 6.5 has to be checked by using instruction ANI20. Why it is written ANI20? Because we want to check this one only. So this is 0, this is 0, this is 1, this is 0, this is 0. Sorry, this is 0, 0, 1, 0, 0, 0, 0, 0. So it means 2, 0. So what we want, whatever is the content of accumulator, it will be ANDed with 2, 0. Whenever it is ANDed with 2, 0, if this bit is 1 in that accumulator, it shows that 6.5 is pending. If this bit is not 1 in the content of accumulator, it means this is not pending. So if there is no 0, what it will do, it will move to the next. And what is next? Next is get the bit, meaning thereby take the bit pattern of B into the accumulator, enable the RST 6.5 by setting D1 equal to 0. And then we are going to do OR operation with 08 so that it is going to enable the flip-flop of 6.5. And then we will set interrupt mask, and then we will jump to the service subroutine, which is meant for 6.5. So read interrupt mask is going to check the pending interrupt. ANI20 masks all the bit except the D5 to check the pendency of 6.5. If D5 is 0, the program control is transferred to the main program. And if D5 is 1, it indicates that RST 6.5 is pending. So if RST 6.5 is pending, what we will do AND operation with 0D. Whenever we are going AND operation 0D, it means we want to set D1 is equal to 0. Whenever we want to set D1 is equal to 0, let us go and check. We want to set this D1 to be equal to 0. So it means 1, 1, and 1, and this should be 0. So 8, 4, 12, and 1, 13. 13 means D. So that is why we are doing it with the 0D. ANI instruction with 0D. So this is going to set the D1 bit equal to 0. And whenever D1 bit is equal to 0, it is meant for the SIM instruction. And then we are going to do ORI instruction, that is OR operation with 08. ORI is going to set the bit D3 is equal to 1. What is bit D3 equal to 1? This bit D3, because we want to set it enable. We want mask set to be enabled. So that is why we are going to make it enable. So this will become 1 and this will become 1. And the rest of the, this will become 1 and this will become 0. And rest will be 1. So that is why we have done ORI to set D3 bit equal to 1. So while doing ANI 0D, it is going to set the D1 bit. While doing ORI, it is going to set D3 bit, and then only the set interrupt mask will be enabled. And this set interrupt mask is going to enable the RST 6.5 without affecting the any other flag. And then it will jump to the service subroutine, which is meant for RST 6.5. So this is how with the help of instruction EI, with the help of instruction SIM, with the help of instruction RIM, EI is going to enable all the interrupt. SIM is going to mask or unmask or make make the availability of the interrupt, different interrupt, RST 7.5, 6.5, or 5.5. And read interrupt mask is going to give you the information that which interrupt is pending. So this is the example by which you can know the pendency of the interrupt.